The climate crisis is real. We're at a point now where we're essentially having to make decisions on how to move forward. So rather than working on environmental problems that are really large scale, I'm actually focusing in on microbes at a really tiny scale, but they have the capacity to carry out large-scale processes that influence climate change. Microorganisms pretty much rule the world. They are responsible for functions that affect climate change. Microbes also control our ability to improve water quality and to address contaminant issues. So the research that we're focusing on here at the long-term fertilization and mowing plots is focused on understanding how long-term nutrient additions from agriculture or other industries that end up in particulate form in the atmosphere and then can rain down or get dry deposited on wetlands that are far away from those sources. The consequence of that is that these wetlands that are typically nutrient limited are now being fertilized. And why we care about that is because wetlands are known to store a lot of carbon. But once you add this nutrient addition, what can happen is that microbes will increase their activity and they can actually use the carbon for energy and then respire it or breathe out carbon dioxide. And so you're left with the carbon that was stored in the soils now is getting released back into the atmosphere. That essentially creates a blanket around the Earth, making it much warmer. It affects the intensity and frequency of storm events to sea level rise. And so we need to understand how microbes are actually responding to this so that we could manage particular ecosystems like wetlands in order to increase carbon storage capacity and then decrease carbon losses. I'm really humbled by receiving the 5-year award. Working at ECU has made it possible to work across disciplinary boundaries, and that is key to being able to address some of these really wicked environmental problems.